Hello, and thank you for taking the time to listen to my recap of my presentation at TIDES US on scalable drying thermally sensitive materials using electrostatic drying technology and solvent applications. In the interest of time, I will provide a shortened overview of the process. Electrostatic drying is based conceptually on conventional spray drying, but has some modification and differences that make it applicable to thermally sensitive materials. The material to be dried is fed through a two-fluid nozzle that atomizes the feed into droplets that are then electrostatically charged. The droplets are then carried through the system in the cyclonic flow of the drying gas, which in the case of electrostatic drying is nitrogen. With the electrostatic effect and the cyclonic drying gas flow, the droplets are able to be dried into powder particles at moderate process temperatures. These dried particles are then separated out from the saturated gas stream and collected in bulk product appropriate containment. Electrostatics benefit the polar dry process in several ways that are well supported by literature on their own. The first effect is the strong electric field within the drying chamber that polarizes the droplets, moving the solvents to the outside of the droplet where they can evaporate off easier. Another benefit is the Coulombic forces that move the droplet faster than the surrounding bulk gas flow to move the droplet out of the saturated vapor cloud, allowing it to dry constantly. In addition to this, the electric field moves the vapor cloud across the gas flow and away from the droplet. Lastly, the charged droplets repel each other, resulting in a larger spray bloom that allows for increased mixing with the drying gas. The exact contribution of each of these effects to the improved drying is still being actively researched by our research groups within our organization. Electrostatic drying provides several key benefits in the manufacturing of biotherapeutics, including peptides and oligonucleotides. These include particle formation and engineering in both aqueous and solvent-based systems, with or without excipients, and in a continuous process. Their moderate temperatures applied ensure high purity and therapeutic activity in the product of interest, while the electrostatic effect and overall process ensures proper solvent and moisture removal for the end product. A study was performed with the consortium Lyle Hub through Purdue University to compare BSA, which is a commonly utilized biotherapeutic surrogate, with and without excipients, and dried by lyophilization and electrostatic drying. As you can see, the continuous process of electrostatic drying provided a powder that was on demand, meaning you were able to collect the powder as the feed is actively being dried, with a total time of less than 4 hours to process a 1,000 milliliter batch. The lyophilization cycle time for only a 200 milliliter batch was 70 hours. While the study was performed on an aqueous-based system, similar time savings could be applied to solvent-based systems. Noteworthy is that both drying methods tested provided comparable stability and integrity of the dried product. This too can be applied to solvent-based systems. The images here are taken from the same study as my last slide and provide insight into the powder formation and engineering capabilities of electrostatic drying that are not possible with lyophilization. Powder particles are able to be formed and engineered to a certain extent with electrostatic drying, pending formulation and process conditions, of course, while lyophilized cake typically needs to be further processed down by particle size reduction equipment to form a powder. Post-processing milling often leads to larger product losses and adds an additional process step to the overall product life cycle. In solvent application, another step that can be eliminated with electrostatic drying is the step of concentration. While solvent removal is often needed prior to lyophilization, this is not the case with electrostatic drying. Together, the removal of the concentration and post-drying steps that are commonly a part of the lyophilization workflow provide for faster, more efficient processing. Fewer steps afford a time and energy savings that are beneficial to the overall product life cycle. An internal case study was performed using 1% BSA and 50-50 acetonitrile in water solution to assess the effectiveness of electrostatic drying to remove the residual solvent from the product at moderate temperatures. As shown in the graphs, the residual solvent for both laboratory and production scale was consistently below the ICH limit of 410 ppm. At the laboratory Polar Dry Model 1 scale, the system is a once-through system that exhausts the drying gas after it has been saturated with the evaporated moisture and solvent. However, at the production scale, the saturating drying gas flow is conditioned to remove both solvent and water, then recirculated to allow for a more sustainable process. With both once-through and recycling systems, the residual ACN is maintained below ICH limits in the finished powder. There was also a trend observed that lower temperatures correlated with lower acetonitrile retention by the powder. Further research on this observed correlation is ongoing. In addition to the effective removal of residual solvent, the process provided effective moisture removal even at temperatures that are moderate enough to prevent any product degradation or impurity formation. Moisture contents below 6% were achieved on 2 different scales of recycling gas systems, proving the capability of meeting typical product moisture specifications at production scale, while still removing solvent appropriately even at gas recycling systems. Lastly, recognizing that powder yield is another critical aspect of the drying of thermally sensitive materials. The powder yields attained in this study were above 90% at production scale. This is for a process that generates powder without the need of further milling, where losses could exceed 10%. In summary, electrostatic drying provides a method for drying of thermally sensitive materials, such as both oligonucleotides and peptides. The method is capable of both moisture and/or solvent removal in low solids content applications, eliminating the need for evaporation and/or concentration, as well as post-processing steps such as milling, while maintaining powder requirements of low impurities and degradation, but still providing high yields. Thank you again for listening to my TIDES US Talk recap. As this provided only a short snapshot of what the electrostatic technology offers, please feel free to reach out to us to speak with one of our team to learn more. Thank you again.